that are famous enough that we get to name them, and we're going to go through, again, just a few of them. The first random variable that's famous enough for us to name them is the Bernoulli random variable. Okay. So for a Bernoulli random variable, you can only take two values. Okay, so you can use it to model, say, like a coin toss, or whether or not a switch is open. Anything that's either like yes or no, heads, tail, 1, 2. If you only have two options, we use the Bernoulli random variable. Okay. And then because you only have two options, we'll set the first option to 0, the second option to 1. Okay. So usually the 1 is for the thing we want to model. So we want to model if we get heads, then heads would be assigned the value 1. Okay. And the probability that the item occurs is p, which means what's the probability that it doesn't occur? It would have to be 1 minus p, using the complement rule. So again, it's for something happens or it doesn't. Yes or no. So the probability that occurs is p, and we call p a parameter. We haven't seen this word parameter yet before. It's just something that defines our distribution. The probability p can be between what two numbers? 0 and 1? So for our first example, we're going to let x be a Bernoulli random variable, and we're going to find the expected value of x and the variance of x. And well, at this point, we have the PMF. We have each x value and its probability, and we know how to find expected values if we have that. So the expected value is the first x value of a 0 times by its probability plus the next x value of 1 times its probability, which gives me p. So the expected value for a Bernoulli random variable is p. Now if I want to find the variance, so let's find the expected value of x squared. So I take each x value square and times by the probability. So 0 squared times 1 minus p plus 1 squared times p. So this just gives me p. So finally, if I want to find my variance, I need to do expected value of x squared minus the expected value of x quantity squared. So expected value of x squared is p minus p squared. And we usually factor this. How would you factor this? P times 1 minus p. So very important outcomes for us. The expected value of x is p, and the variance of x is p times 1 minus p. So we'll use formulas that look like this a lot throughout the rest of the class. And this is where it all comes back to. So for the next example, I want to toss a bias coin once and let x be the number of heads that I get. I know from past experience that the probability of heads is 0.4. Find the expected value and the variance. Notice I'm only tossing the coin once. So what is my p-value? 0.4. Since I'm interested in the number of heads, that's the probability of heads. So my expected value of x is p, so 0.4. And the variance of x is p times 1 minus p. So 0.4 times 1 minus 0.4 should give me 0.24. So, questions? Notice this is very simple. There's not very much I can do with this. Okay? I mean, it's 2 lines. You're done with the problem. Won't take very long. Any questions on it? So again, this is if you have something that's either like a yes or no, but you only do it once. Okay. That's probably not very interesting to have something that you only do once, right? So that's why we're going to extend it to what we call the binomial distribution. Okay. So let's consider a student taking a multiple choice quiz. Each question has 3 choices. Assume that a student is blindly guessing. We will let x be the number of right answers. So if we have the student take a quiz with just one question, if it's just one question, could that count as a Bernoulli random variable? Okay, they're either right or wrong, and we're only doing one. So this, to start with, would be the Bernoulli. Okay. So for them to get a question right, okay, what would we say the value of x is? Okay, so again, x is the number of right answers. So if they get the first one right, then their value of x is 1. And the probability of getting one question right is 1/3. Because there are 3 choices, they are randomly guessing. Okay, if they get the question wrong, how many questions do they have correct? 0, and the probability would have to be 2/3. So that was very easy to fill out my probability distribution function because I only had 2 choices. Okay. So now what if the student takes a quiz with 3 questions? Is it Bernoulli anymore? Okay. So this is not Bernoulli because I'm doing it 3 times. Okay. So we're going to fill out this table of probabilities. So for my sample space outcomes, if I have a right, 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 okay, think back to how we found our probabilities in the past. Okay, how would I find that probability? I need a right and a right and a right. So what do I need to do with the probabilities? Multiply. And the probability for each one is 1/3. So it's going to be 1/3 times 1/3 times 1/3. So 1 out of 27. How could I rewrite this using exponents? That is 1/3 to the power of 3. Okay. And my value, well, we can do that in a minute, I guess. Okay, what if then I want a right, right, wrong? What's the thing that changes? Okay, so I need a right, which is 1/3, times the next one is still right, so 1/3, but the probability of a wrong is 2/3. And so if I rewrite it using my exponents, this is 1/3 to the power of 2 times 2/3 to the power of 1. If I have a right, wrong, right, then this would be 1/3 times 2/3 times 1/3, which gives me 1/3 to the power of 2 times my 1/3 to the power of, 2/3 to the power of 1. And you'll notice I filled out the rest first just to save us time in writing them down. Okay, look through it. Do you see the patterns that are happening? Okay, so if I have, my next one's like 1/3, 2/3, 2/3, so I have 1/3 to the power of 1 and 2/3 to the power of 2. Let's go through this table and fill out the value of x for each one. So remember, x is the number of correct answers. So my value of x for the first one is 3. Next one is 2. Next one, 2. My next one is 1. Okay. Then 2, 1, 1, and 0. So look through this. Like, if you haven't seen the binomial distribution before, like, what kind of patterns are you noticing? Are you noticing anything yet? So keep looking through patterns as we're going through this, as we fill this out. So for my values of x, my possible values are 3, 2, 1, and 0. Okay. How would you find the probability of getting this 3? So it's just my 1/3 to the power of 3, which is 1 out of 27. Okay. What about for the 2? What do I need for the 2? Okay. I need this one, and that one, and I need to add those probabilities together. Okay. What do you notice about them going through? Are they all about the same? Okay. Looks like they are all the same. It's the 2 out of 27 plus 2 out of 27 plus 2 out of 27, which gives me 6 out of 27. Okay. What about for the 1s? Okay, the 1s are all 4 out of 27. And there are 3 of them. So that gives me 12 out of 27. And finally, for the 0, the only way I can get a 0 is if I have this last one. So it is 8 out of 27. So that's how we would do the probability distribution, knowing what we've known in the past, or using our things we've discovered in the past. Okay. So let's say we want to rewrite our probability distribution using exponents and multiplication. Okay. So for the value of 0, that was 1/3 to the power of 3, right? For the value of x equals 1, okay, each of these 1s, okay, what is it? It's 1/3 to the power of 1 times 2/3 to the power of 2. And how many of them did I have? 3. So you can write this as 3 times 1/3 to the power of 1 times 2/3 to the power of 2. What about for the value of 2? How many of 2's did I have? There are 3 of them, and each one had the probability of 1/3 to the power of 2 times 2/3 to the power of 1. And the very last one, to get 3 right, you had to have 1/3 to the power of 3. And that means I did something wrong here. Okay, to get 0, what was the probability to get a 0? It was 2/3 to the power of 3. Okay. Could I rewrite this 1/3 to the power of 3? Is anyone going to object if I rewrite this times 2/3 to the power of 0? Does that change anything? Okay. And coming back up to the probability of 0, I could rewrite that as 1/3 to the power of 0 times 2/3 to the power of 3. Right? Doesn't change anything. So I want to ask you some questions to help you look for the patterns. So like, what do you notice that our exponents always add up to each time? 0 plus 3 is 3, 1 plus 2 is 3, 2 plus 1 is 3, 3 plus 0 is 3. So that's kind of interesting. They all add up to 3. Let's compare the exponents on the 1/3 to the x values. What do you notice? When x was 0, the exponent on the 1/3 was 0. X is 1, the exponent on the 1/3 is 1. 2, 2, 3, 3. Do you think that's coincidence? Okay. So it's not coincidence. So let's be specific. So for example, for the value of x equals 2, why do you need that exponent to be the 2 on the 1/3? That's the number of right answers you need. So if I want 2 right answers, then I need the probability of the first right answer times the probability of the second right answer. Okay, why did I have to multiply the probabilities by 3 for that x equals 2? Okay, so why did I need that 3? We had 3 ways to get x equals 2. Does that kind of remind you of anything? Like how many ways to get what you want? The combinations that we talked about. And in this case, we said we don't really care if it's right, right, or right, wrong, right, or wrong, right, right. Like you're still getting 2 correct answers. So that's why it was a combination with order not mattering. Now let's say the student has to take a quiz with 10 questions. Each question still has 3 choices. So how many possible outcomes are there? How would you do this problem based on what we learned in section 1.7 with our counting techniques? What do I need to do? So how many possible outcomes are there? Okay. How many outcomes are there for the first question? You can be right or wrong. So for the first question, you can be right or wrong. For the second question, you can be right or wrong. Third question, right or wrong. All the way up to the last question, you can be right or wrong. So my total is 2 to the power of 10 since there are 10 questions. So that gives me 1,024. Okay. Any of you guys want to fill out the table to find with 1,024 probabilities? Probably not. Okay. So let's come up with our formula to find our probabilities. Okay. So let's say we want to get k questions correct. Okay. What do you think we need? Based on like what we've done, patterns you saw on the previous page. Okay, you don't have to start necessarily at the beginning, just like what are you going to need? So if I want k correct, okay, I'm going to need 1/3 to the power of k, because I need to get k of them correct, which means if I get k of them correct, how many do I have to get wrong? Or in this case, 10 minus k. Since I have 10 questions, if k of them are correct, that means that 10 minus k are wrong. Okay. What else did we need? Okay. The number of ways to get each value. So like if k is 5, how many different ways can I get 5 questions correct? I could get like right, 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 or right, wrong, right, 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 right. Okay, so how many ways do we do that? And we learned that we can use what's called the combination. Okay, how many total questions are there? 10, and I need to figure out how many ways I can get k of them correct. Okay. So this is the number of ways to get k correct. So that's my combination. This 1/3, what does that account for? This is the probability of k correct. And then finally, this 2/3 10 to the minus k, that accounts for the probability of 10 minus k wrong. So if k of them are correct, then we also need the rest of them to be wrong. So let's start filling out this table using the formula that we just came up with. So for x equals 0, let's first figure out what is the number of ways to get x correct guesses. So that would be 10 choose 0, which is going to be 1. Okay, and then for the probability, so it's going to be my 1 times, well, I need 1/3, and I need to get 0 correct, and then 2/3 for the probability of getting wrong, and I need 10 to be wrong. So this would give me 0.0173. How do I find the number of ways to get 1 correct? That would be 10 choose 1. Everyone remember where it is on your calculators? It gives me 10. So there are 10 ways to get it 1 correct. So it's going to be 10 times 1/3. I need to get one of them correct. And if I get 1 correct, how many do I have to get wrong? I have to get 9 wrong. So 0.0867. And we just go through this table. So for the rest of this class, just go through it and fill out what you count on the table. So the next one is going to be 10 choose 2. 45, so it's going to be 45 times 1/3 to the 2 times 2/3 to the 8. So 0.1951. So do you have any questions on how you're going through and filling out this table? Okay, seems pretty simple. So this is leading us up to what we call the binomial distribution. We will start on that tomorrow. Okay. Remember that for tonight you need to finish your sections, everything for chapter 2, so 2.3, 2.4, and 2.6, and bring that tomorrow.